Hello. In this lesson we're going to look at using complex numbers to establish trigonometric identities. You might remember that sometimes trigonometry can be quite complicated. There's lots of identities to remember, ways of simplifying formulas. A lot of that gets a lot simpler with complex numbers. And the key reason for that is Euler's formula, e to the I theta equals cos theta plus I sine theta. So that on the left-hand side we've got an exponential, and the rules for manipulating exponentials are much, much easier than the rules for trig functions like cos and sine. Let's do an example of how that works. If we raise both sides to the power n, on the left-hand side we get e to the I theta to the n. That's the power of a power, so that simplifies very easily to e to the I n theta, which is of course cos n theta plus I sine n theta. On the right-hand side, we get cos theta plus I sine theta to the power n, which is a complicated trigonometric expression. If I plug in a particular value of n, I'll get some trig identities. So let's do n equals 3. Plug in n equals 3, I get e to the 3I theta on the left. Well, that's cos 3 theta plus I sine 3 theta. On the right, I get cos theta plus I sine theta all cubed. Now I'm going to expand out that bracket, essentially using the binomial theorem. I get the first term cubed, that's cos cubed theta. Then I get 3 times the first term squared plus the second term, that's 3 cos squared theta times I sine theta, plus 3 times the first term and the second term squared, that's 3 cos theta I sine theta all squared, plus the last term cubed. Collecting up the real terms, well, the first term is real, the second term is imaginary, so I'll ignore that for a while. The third term simplifies to I squared times sine squared theta. I squared is minus 1, so that gives me minus 3 cos theta sine squared theta. Now I run along that expression again, looking for the imaginary terms. The second term is imaginary, that's 3 cos squared theta times sine theta. And the last term is imaginary, it's got an I cubed in it. Well, I cubed is I squared times I, that's equal to minus I, so I get minus sine cubed theta altogether. Now I can equate real and imaginary parts. Setting the real parts equal gives me cos 3 theta equals cos cubed theta minus 3 cos theta sine squared theta. Setting the imaginary parts equal gives me sine 3 theta equals 3 cos squared theta sine theta minus sine cubed theta. So one complex identity gives me 2 real identities, and I'm done. Now clearly that's going to work for any value of n, although some of the expanding out the binomials would get more and more complicated for larger values of n. But in this way you can get multiple angle formulas. The take-home message is that you can go back and forth between trig functions and exponential functions. Some things are much easier with exponential functions because the identities are easier. Some things are easier with trig functions because they're basically more familiar and useful for working with problems with circles and triangles.